forces of flight. We've talked about lift. So lift is that force that sort of pulls up or pushes up on the airplane, gets it off the ground. But we have a force that's opposing lift, and that's the weight of the airplane being pulled down by the Earth's gravity. So lift and weight pulling upwards and downwards, and then you have thrust pulling the airplane forwards, but you have the drag of the air flowing around the airplane and being disturbed, working against that thrust to slow the airplane down. And as an airplane flies along in level flight, all four of those forces are in equilibrium. Lift is equal to weight, thrust is equal to drag, and the airplane just flies along in a straight line.
You're a happy camper.
Exactly. Now, we've talked a little bit about lift and what happens when you increase the angle of attack. As you increase the angle of attack, of course, we talked about you get more and more lift until you get to that point I talked about earlier where the flow starts to separate over the top of the wing, and then the wing stalls, you get less lift. So that angle of attack where you get the most lift and just before the stall is called the critical angle of attack, because that's where if you push it past that angle, the wing will stall. But that is where you get the most lift out of the wing. And in mathematical terms, they call that the coefficient of lift. And you'll see on some of these charts, for example, a figure 5-5, you'll see the amount of lift is this red line comes up and it's labeled CL for coefficient of lift. And where that red line comes up, you get the most lift, that's where the wing stalls, and they say that's CL max. So coefficient of lift max is just a fancy way of saying that's where you get the most lift out of the wing, okay, relative to the speed of the air. Now, something else to be aware of, figure 5-6 here. So as the angle of attack increases, we make more and more lift. Anytime you create lift, you also create drag, because since you require an angle of attack, the lift always acts perpendicular to the wing. Mm-hmm. So if the wing is angled like this, relative wind is hitting it, the lift is going up.
It's not straight up.
It's going
like
up,
10,
but it's also
degrees.
going back because it's perpendicular to the wing, and the wing is angled up.
Right.
So the portion of that lift that's angled backwards is experienced as drag. Okay? And we call that induced drag because the act of creating lift induces that amount of drag. You cannot have lift without having drag because of the angle of attack. So, and on here in figure 5-6, you will see that as the speed increases, the induced drag decreases because your angle of attack decreases.
It's getting flatter.
So the more speed you have, the less angle you need to create the amount of lift that it takes to keep the airplane airborne, and the induced drag decreases. So you might think, well, isn't it more efficient to fly fast then? Well, to an extent. But you'll also see here the green line on figure 5-6 has parasite drag. Well, parasite drag is just the drag of the whole airplane structure moving through the air. The fuselage, the wing, the tail, the landing gear, all of it. And as you move faster and faster, the air sort of pushes against the structure more and more, and you get more what's called parasite drag. So the most efficient speed to fly is where you have the best balance between induced drag and parasite drag. So you have a low enough angle of attack that you're not creating a whole bunch of drag that way, but you have a low enough speed that you're not creating a whole bunch of drag by pushing the airplane through the air faster than it needs to go. And you'll see that on this figure 5-6 here. If you take the induced drag and add it to the Parasite drag, you get another curve above it, which is total drag, and you'll see how that goes down and down and down as the induced drag goes down. But then at a certain point, the Parasite drag starts increasing exponentially, and as it does that, the total drag starts back up again, because now you're getting more and more Parasite drag from the speed that the airplane is moving through the air. So you'll have a point here, and it's pointed out here as minimum drag, where you're
being efficient with it.
right. You're being the most efficient because you have the induced drag plus the Parasite drag is the least. So if you go slower than that, you get more induced drag and you get more drag overall. If you go
So
faster
is that why
than
they
that,
define a cruise speed for a plane?
that's
Is that usually right in that happy zone right there?
that's part of it. Usually the cruise speed is considerably higher than that, but if you want to be most efficient, you could cruise at that.
So do the manuals tell you what that speed is, or is that something you can actually feel in the plane?
A little bit of both.
I was just wondering, when you were talking about that perfect speed, when you're flying, can you just like, okay, I can feel it's getting, I got to cut back even though I'm not at cruise if I want to save the most gas kind of thing.
Mm-hmm.
Just was curious, can you literally feel that in the seat of your pants?
You can to a certain extent. As you gain more experience as a pilot, you'll get more able to feel that. Where you are the most able to feel that is when you're on landing approach, and you'll notice that if you go too fast, it seems like you'll just be coming down faster. But if you go too slow, you'll feel like you're also coming down faster. Well, that's
So there's a happy.
there's that happy zone where you're creating the least amount of drag for the amount of lift, right at this lowest point of the total drag curve on this figure here. And you asked, is that cruise speed? Well, no, not usually. Usually we're going faster than that at cruise because we have the engine power to go faster, and we prefer to go faster if we want to get somewhere. But this speed is the best glide speed. So if you notice on chart 5-5, where it has this green line that's marked L over D, that's lift over drag. So that's the ratio of the amount of lift we're creating to the amount of drag we're creating.
Mm-hmm.
Well, that is essentially this total drag curve from figure 5-6. They've just plotted it upside down because it's easier to relate it to some other things like coefficient of lift and coefficient of drag. So you'll notice that at the bottom of the total drag curve on figure 5-6, that's where we get the least drag. So that is our best lift over drag ratio. And if you look on this chart, you'll see that is plotted as L over D max, or L/D max. And that is our best glide speed. So that is, if the engine is not producing thrust, that is the speed at which we'll make the most forward progress through
So we have one of
through
those
the
power
air.
out scenarios, that's the speed we
Exactly.
want to be dialing in.
Exactly. And when we come into land, that's also the speed we're going to use most of the time, because that gives us the best glide range to make the runway, and that also gives us the most flexibility in terms of being able to slow the airplane down a little bit or speed it up a little bit on the landing approach. Now when we come in, for example, for a soft field landing or a short field landing where we want to minimize the amount of energy that the airplane has at touchdown, minimize the speed we're touching down at, we might come in a little bit slower than that. But if we come in slower than that, that means we're creating more drag, and you'll actually notice we come in steeper even though we're coming in slower.
Okay. Makes sense.
So the best L over D speed, or the best glide speed, is going to be fairly close to the speed that we fly our landing approaches at in most airplanes.
Okay.
And you can get into a whole bunch more math here if you really
Yeah, that's the
want
part
to.
that made my brain hurt when
Yeah.
I was reading through it.
Yeah, so if you want to get into more of the math, there's a lot more of it here on page 5-5 into the subsequent pages, but in terms of understanding the concept, that's the important part. Now it does talk here about ground effect. So when an airplane flies close to the ground, it actually gets a better ratio of lift to drag than it does flying away from the ground. And that's detailed here. And this is why when you are coming into land and you're just above the runway, you'll notice the airplane is coming down, coming down, coming down. Then you get just above the runway and it seems to float there. I mean, in fact, we call that floating, where you get just above the runway.
Seems to smooth out there too.
Seems to smooth out. The airplane kind of stops descending, and it just seems to want to fly and fly and fly until it finally touches the ground. And part of the reason for that is ground effect. And that is essentially the airflow around the wing interacting with the ground. So we talked about how you get higher pressure underneath the wing and lower pressure above the wing, right?
Mm-hmm.
When you get close to the ground, that high pressure underneath the wing is also, it's pushing against the wing, it's also pushing against the ground. So that
So all
air,
those layers we talked about.
exactly. So those sort of layers of air, or pressure levels of air, sort of get squeezed in a way between the wing and the ground, and you get higher pressure under the wing. Your flow over the top of the wing, your low pressure is the same, but as you get close to the ground, that high pressure below the wing actually increases.
Right, because it's getting compressed.
Exactly. And that, as you get close to the ground...
Don't have ground effect, but that's a good explanation.
Yeah. So, because the high pressure air is getting compressed even more, it's now... the difference in pressure between the bottom and the top is greater, because you now have even higher pressure below relative to the same low pressure you always had above, and you get more lift, and therefore you can reduce the angle of attack, and when you reduce the angle of attack, you reduce the induced drag, and that improves the lift to drag ratio.
And it just keeps floating.
Just keeps floating and floating.
Yeah.
Now this can have an interesting effect on takeoff, because if there's something that disturbs the airflow on the top of the wing, so say ice, for example, or snow, this is why we don't take off with ice on the wings, because if there's ice on the top of the wing, it disturbs that clean flow. And when you take off, you might initially get off the ground, but then when you get up where you're getting out of ground effect, and ground effect is mostly effective within about one wingspan of the ground. So, say that's the wingspan of the airplane on the table there. So if I mark that height, put the airplane at that height, it's roughly below there that you start to experience ground effect. And as you take off and you get up to that one wingspan above the ground, you start to lose that ground effect. And if there's ice, or even I've even heard of it happening where the airplane has just been painted and there's a paint ridge that they forgot to smooth out that's disturbing the airflow. And this depends on the airfoil, and some airfoils are more sensitive to this than others. The Ch.5 has a very forgiving airfoil that's less sensitive to this sort of thing, but some very fast airplanes, some home builts that are trying to fly fast on a small engine, use an airfoil that's much more sensitive to disturbances. And there have been cases where just having a paint job disturbs that flow enough where they get up to the top of ground effect, and they suddenly, they're flying along just fine, and then they suddenly stall, because as you get out of ground effect, you have to increase the angle of attack to create the same amount of lift, right? Because you're losing that ground effect. Well, as you increase the angle of attack, you're getting closer to the stall. And if you took off, if you were already close to the stall in ground effect, and now you climb out of ground effect, well, now you've just increased that angle of attack more,
Yeah, I
And-
remember reading when you're taking off, sometimes it'll come up because of ground effect, but you don't have the speed to really climb.
Exactly.
And if you keep trying, you just pretty much float back down to the ground.
Exactly.
So I think I remember reading in there, you get off and you get in ground effect and you stay there while you pick up speed.
Exactly.
And then once you're up,
Right.
if you pop off the ground too quick, you
Right.
keep the nose down and get your speed
Right.
up until you're well past that.
And that's when we're taking off on short runways. We want to pop the airplane off the ground as soon as we can.
So you don't have the friction and you can pick your speed up quicker.
Exactly.
That's why those bush plane guys do their thing.
Right. Exactly. So that if the runway is soft, so down at Brooklyn we're flying on a grass runway. So when we get into springtime, that runway is going to get soft. And when we take off, as you say, when you're trying to accelerate on wet grass,
A lot of friction.
A lot of friction, you can't accelerate as well. So what you want to do is you want to pull the airplane off the ground
Just a tiny bit.
just a tiny bit at as slow a speed as you possibly can to reduce that drag. And then once it's off the ground, you stay just above the runway in that nice cushion of ground effect there and accelerate to the speed that you should climb at, and then you climb off.
So you're not always coming off the ground at your V1 rotate speed. You're coming off, probably went too far there, but at that speed where you're supposed to be able to fly.
Yeah.
You're getting off the ground before that because of the ground
Right.
effect and using it to your advantage.
Right. And when you talk about V1 rotate, that's something you hear in airliners, and that has to do with a whole bunch of other stuff,
Yeah.
having to do with having more than one engine, and that gets into a whole other can of worms.
Yeah,
But,
we don't want to go there, but I know that's the speed where you can take off and fly.
Yep.
So.
Yep. So that's ground effect in a nutshell. When we talk about we've talked about a little bit about the airplane pitching up in terms of increasing the angle of attack. Although it might be said that the angle of attack doesn't necessarily have to do with the angle that the airplane is relative to the horizon. Because, for example, if we take this airplane and we head it straight down, and we try to change direction, so if we pull up,
Install
now the airplane is trying to change direction. If you try to change direction too quickly, even if you're going down, the harder you try to change direction, the more angle of attack you get on that wing.
Gotta
Because
give
the harder it's trying
You
to.
have to give the wind time to catch up.
Exactly, because the airplane has mass. It can't change direction instantaneously. So in order to change direction, it has to push on that air. And the harder it has to push on that air, the more angle of attack it takes. So you can actually stall an airplane pointed straight
dive,
down,
yep.
which is something that you
Yank
probably
the stick back too
Yeah.
fast and it'll do crazy things on you.
you probably won't experience that on firsthand unless you do aerobatic training. But when I did my aerobatic training, we intentionally sometimes did maneuvers where we would do a stall, not pointed downwards, in order to do various aerobatic maneuvers. But it's something to realize that just because your nose is not pointed at the sky, that doesn't mean you
Everybody
can't
thinks
stall.
this is the only thing that stalls you is when your
Yeah.
nose too high.
No, it's not about where the nose is pointing. It's about how hard you're trying to change direction. So when you're at a slow speed and the nose is pointed high, you're essentially trying to change direction and climb, but you can't because you don't have enough speed.
Yeah.
And the more you try to change direction, the more angle of attack you need. And when you get to that critical angle of attack, well, the wing just doesn't have anything left to give you anymore. But for the most part, when we practice slow flight or stalls, we will practice it in level flight, which means the nose is going to come up as we get closer to a stall, and as the nose comes up, we call that pitching. So the nose pitches up or pitches down. When we turn left or right, we call that rolling left or right, and if we want to turn left or right, take the nose left or right, that's yaw. So
In the RC world, it took me a long time to understand yaw. Just turn left or right. And the yaw just messed with my brain.
yeah.
But I totally understand it now. It makes sense.
So when you yaw the airplane, it's as if you're pivoting around like if we put a pin through this airplane, this little paper airplane, and pivoted it, that pin would be vertical,
Right.
and therefore we call
vertical
yaw the
axis.
vertical axis. If we wanted to pitch the airplane, if we stuck a pin through the airplane sideways, we could rotate it around that pin, and that would be pitch. And since the pin is lateral, is side to side, we call that the lateral axis, pitch. And then likewise, if we want to roll the airplane left or right, if we stuck a pin through the airplane nose to tail and we rotated it around that pin,
The long way.
the long
With that-
way, nose to tail,
The
that would-
longitudinal.
that would
the
be-
longitudinal. That's
that
That's
would be
how I
roll.
remember
that
it.
would be longitudinal axis.
that's how
Yep.
It took me a few,
Well,
because it doesn't. It seems like vertical is this.
but it's not.
It's
is it?
and that's one
Yeah.
of those things for me.
Right.
I've known this already, but I still have to stop and think about it because I just tell myself longitudinal. That's the roll
Yep.
because it's the long way of the plane,
Yep.
and that's how I remember it now. It's longitudinal. The vertical is easy because that's this way, so
Yeah.
that leaves the lateral as the roll. So for you guys, that's how I learned it. The longitudinal, you put it long way down the anyway.
Yep.
Sorry to interrupt.
That's that's
That's a
good.
tip of mine how I learned it.
Yep.
Sorry, we've got vacuum cleaners going by outside if you hear that. Sorry. We'll talk a little louder.
Yeah. So something else that we talk about is stability of an airplane. So stability is how much the airplane wants to stay right side up, right? So
That's
there's
a good thing.
there's two kinds of stability that we talk about. That's static stability, which is how much the airplane resists being tipped over to one side or the other, right? Then we have dynamic stability. So dynamic stability is if you do manage to disturb the airplane, how much does it want to come back to level, right?
Yep.
So
That's where the dihedral helps.
that's where the dihedral helps in roll, and that's where having the airplane, that's where the center of pressure moving that we talked about earlier helps in pitch. Because as the airplane, if you nose the airplane down, it'll tend to speed up. Well, that'll tend to make the airplane want to pitch back up. If you pitch the airplane up, it'll slow down. That'll tend to want
You
make
start
the airplane
porpoising.
want to pitch back down. Now, when we talk about if an airplane is flying level and it just wants to keep flying straight and level, we would call that positive static stability, right?
Mhm.
So it just wants to keep going in a straight line. Versus if you're flying an airplane, maybe you've had an RC airplane like this in the past, where if you let go of those sticks for even a minute, even a second, it's rolling off and turning one way or the other. Well, that would be negative static stability.
I usually create that. Yeah, I know. Yeah, I've had a few of those. Warbirds are notorious for that.
Yeah, well, in military airplanes, warbirds, and modern fighters are deliberately designed that way to make them more maneuverable. And the other kind of stability is dynamic stability. So that's how much the airplane wants to come back to level after you've tipped it one way or the other. And so if you roll the airplane one way, and then the airplane wants to, maybe because of its dihedral, or it can also be because the center of gravity is below the wing, helps as well. That will tend to bring the airplane back to level, right? We call that having positive dynamic stability, because it wants to.
In the RC world, the planes with dihedral, the trainers, they
Yeah.
always would say, if you get in trouble, just let go of the sticks, and it'll
come back.
eventually come back to itself to a place where you can
Right.
grab it and go.
Because the trainers are designed to have very good, very positive dynamic stability in that
Yep.
way. Whereas if an airplane is dynamically unstable, that would be if you roll it to one side, well, that airplane just wants to keep going over on its back, and you have to work to get it back upright. And again, that would be like a warbird or a fighter
Stunt plane.
fighter plane.
Yeah, my first venture from easy planes to 3D or aerobatic planes
Yeah.
in the RC world, it was a little foam one, and I was so used to just flying without the rudder, just using
Yep.
ailerons and elevator to make a turn.
Yeah.
I went to aileron and just knife edged.
Yep.
It just kept flying sideways. It's like, holy I guess I got to learn my rudder now.
Yeah.
And I learned the rudder real fast. Because
Yep.
I put it in an angle and it stayed there.
Yeah.
You know, it was weird.
Yeah.
But that was a light bulb moment for me.
Yeah. Well, and if that's something else interesting is we talk about positive or negative stability. So positive stability is it wants to come back. Negative stability is it goes further over. If it just stays where you put it, that's neutral stability. That's
Well,
interesting.
that one had it.
Yeah.
That one certainly had it.
And they've got a little graph here on figures 521 and 522 showing static stability, positive, neutral, or negative, and then dynamic stability, positive, neutral, or negative, showing how that develops over time. Part of the way that airplanes create stability, we've talked a little bit about dihedral creating stability in roll. But how do we create stability in pitch, you might ask? Well, we've talked about how the center of pressure moves and where that center of pressure is. Usually the center of pressure or the center of lift when an airplane is in normal unstalled flight is about a third of the way back the wing. Okay? Or maybe a little bit further back, you know, somewhere between a third and a half. So what we do is if the wing is lifting more or less from the middle or slightly forward of the middle, then we want to make sure that our airplane balances right near the leading edge of the wing, just aft from the leading edge. And so if we have the weight, we talked about weight and lift opposing each other. Well, if the weight pulling down is up here and the lift going up is back here, well, the airplane wants to pitch down, right? Well, the thing that prevents that then is the tail. The tail has a negative angle of attack, so it's just like the wing except upside down. It's pushing the tail down. So you have the weight of the airplane pushing the nose down. You have the tail, the horizontal stabilizer, as we call it, the part of the tail that goes crossways, pushing down on the tail, and those are essentially becomes like a teeter-totter, where the wing is the pivot point, and you have the weight of the airplane pulling down on the nose and the tail pulling down on the tail.
Called a horizontal stabilizer.
Horizontal stabilizer pulling down on the tail, and it acts like a teeter-totter around the wing, and it balances nicely like that.
And if it's the slightest bit off, it's a mess.
It can be a mess.
I had a friend, we were trying to dial in his RC plane, and it was flying like it was tail heavy. Like
Yep.
it just, I could barely control it and get it down.
Yep.
And he was nowhere near ready to fly it. And we looked at it, we saw some wings were warped, we got them straightened out. It still flew crazy, and it turned out one of his crashes when he rebuilt it, his horizontal stabilizer had the wrong angle of attack.
Yep.
Put a little bit of tape under there and bolted it back down, flew perfect. And it was
Yep.
like, it seemed tail heavy, but it
Yep.
wasn't tail heavy. It was balanced right.
Yeah.
It's like, holy cow, that tiniest little, that
Yeah.
much made a huge difference in this plane. It was literally uncontrollable.
Yep. Well, and the other thing that's going on there, you talked about the center of gravity.
Right.
And if the center of gravity is too far back, that can make the airplane unstable, because if the wing is pulling up from here and the weight is pushing down from the front, you have a sort of opposition of forces. So you have the weight pulling down and the wing pulling up,
Mm-hmm.
and that wants to pull the airplane's nose down. And then you have the tail counteracting that, right? Well,
It's a
The-
bad recipe.
this is the way we want it. If the weight is too far back, well, now the weight is pulling down at the same place as the wing is pulling up, and it's just balanced there. Well, now the tail's not doing anything. If you've ever tried to balance a teeter-totter
It's
sitting, both people sitting right next to the hinge, well, that's pretty difficult, isn't it? A lot
Yeah.
easier if you move all the way out to the ends to get it balanced right,
right.
isn't it? So the further apart your center of gravity or your center of weight is from your center of lift, the more the tail has to pull down. The more the tail pulls down, you're essentially taking that teeter-totter and you're moving the weights out further towards the end. And as you do that, the airplane becomes more stable. It becomes less efficient because the more downforce the tail is producing, the tail producing downforce, it creates essentially the equivalent of more weight that the wing has to lift because it's pushing down, right?
Mm-hmm.
So it cancels out a certain amount of lift from the wing. So the more the tail is pushing down, the less efficient the airplane becomes. But the less the tail is pushing down, the more unstable the airplane becomes. So when you're designing an airplane, you have to achieve sort of a balance between stability
Somewhere
on
in that
one hand.
1/3 area
Yep.
of the wing for
About between a quarter and a third of the way back is where your center of gravity wants to be, right? Because if your center of gravity and your center of lift are too close, well, then it's just like trying to balance a teeter-totter with two
Yep.
weights that are like right next to each other, and that gets really difficult.
Yep. We have a saying in the RC world: a tail-heavy plane will fly. No, a nose-heavy plane will fly. A tail-heavy plane will fly once.
Yes.
and I've had a few of those,
Yep.
and it's not pretty.
So they have a few more figures on that. Figure 526, 527, and then 532 is talking about more or less the same thing, but just in the vertical axis, the yaw axis. If the airplane is stable in yaw, well, the way we create stability in yaw is by having more area after the center of gravity than forward of it, right?
Mm-hmm.
Because if you have more area forward, well, when you yaw, that nose will catch the air and it'll just want to go around and around and around. And you need a big enough tail that it'll want to sort of weather vane into the relative wind. There was a time, if you don't have enough stability in yaw, an airplane can also it's very difficult to fly. It's kind of like trying to fly.
Because you have no...
Right. It just wants to go everywhere.
I've had those too.
Yep. And that means the tail needs to be bigger.
Right.
So
that's what a lot of the home builders do when they're trying to build a scale plane. They build it to scale, but when you scale it down to RC size, you have to make a bigger rudder
Yep.
to create that. So a lot of times when you see scale RC, they're not really truly scale.
Yeah.
They'll have a huge rudder compared
Yep.
to the real one for that very reason.
And there was a time I was flying an home-built full-scale airplane, and with a friend of mine, and he took me up in this airplane. It was a beautiful little airplane, a lot of fun to fly, but I realized as I was flying it that it had neutral yaw stability. So, we talked about how stability can be positive, it wants to return to where it was. It can be negative where it wants to, so let's talk about it in yaw. So an airplane that has positive stability, if you yaw it one way, it'll tend to want to go back to going straight. If it has negative stability, if you yaw it one way, it'll just go further and further and further out and eventually flip around backwards, and that's not good at all. But you can also have a situation where it has neutral stability, where you can just yaw it and it'll just sit there. And that's what this airplane had. And it was really freaky. Because
If you're not used to it, that would be...
when I was coming into land, and I put it in a slip like we do, so we kick the rudder over and we're essentially presenting the side of the airplane to the wind to create more drag. Well, I had got myself high on landing approach, so I put it in a little bit of a slip to create more drag. And usually, in most of the airplanes I fly, I put the rudder in and I let go of it and the airplane straightens itself out. Well, I put that rudder in, I slipped the airplane, and I stopped pushing on the rudder, and it just sat there. And I had never experienced something like this before in my life, so I sort of sat there not quite knowing what was going on for just a half a second, and then I had to add rudder the other way to straighten it back out again. But I had never flown an airplane before that when I yawed it to, kick the nose out to one side with the rudder, and it just stayed there. That was something else.
So one quick question.
Yeah.
On full-size planes, do they ever have to balance them this way? Where like maybe one wing is... I know it can create problems when you drain one fuel tank quicker than the other.
Right.
But do they factor that in? Because I had an RC plane once. It was just a flying delta wing.
Mm-hmm.
And I could not... It just wanted to pull right, and torque should have pulled it to the left. It just wanted to roll right, and I was fighting it. Come to find out, I held it by the motor in the nose, and it just fell because it was too heavy on one side. I just glued a weight on the other side and solved the problem. But they didn't talk about that much in the book.
Yeah,
I was wondering if that was something that's ever a factor with planes.
It can be. It's more rare. There are some airplanes, like some airplanes have fuel tanks on the wingtips, and those airplanes sometimes have a limitation, like you can't run more than, say, 15 minutes off one or the other. And so some airplanes you can pull fuel from more than one fuel tank at once. Most airplanes have at least 2 fuel tanks, one in each wing. The Chief is a little bit different, actually. It has one fuel tank up just behind the engine, and it has one fuel tank behind the cockpit. So it's fore and aft. Most airplanes have the fuel tanks in the wings, at least one in each wing. Sometimes an airplane will have a fuel tank stuck on the wingtips as well to give it more fuel. And particularly when the fuel is way out at the wingtips like that, as I said, sometimes there's a limitation where if you can only pull fuel from one or the other tank, then, as some airplanes are, some you can do both at the same time, some you have to do one or the other. So in airplanes where it's one or the other, they'll say you can't run off one tank for more than 15 minutes, and then you have to switch to the other one to keep your fuel balanced left to right.
Yeah, that makes sense. But yeah, it wasn't something that was covered a lot in the book. So.
And that can become an even bigger problem in airliners. For example, there was an incident about 20 years ago. There was an airliner sprung a fuel leak on one side, and so fuel was leaking out of the tank in one wing. But in order to keep the airplane balanced, they had to keep feeding fuel from the other tank into that one to keep it in balance.
Just spitting it out.
And just spitting it out. They knew they were leaking fuel out that side, and they knew they were wasting fuel by transferring it over to that tank.
They were doing what they had to do, though.
But they couldn't. They didn't have a choice. If they wanted to stay right side up, they had to do that.
It was the 3 Ps.
Yeah. When we're turning an airplane, the way we turn is we bank it, right?
Mm-hmm.
Well, as we bank the airplane, the reason that we do that is if we just tried to yaw it around, well, the airplane wouldn't really want to turn very much because all that would be turning it. When you turn a car, the tires grip the road and bring you around the turn. Well, when you're in the air, the tires don't have anything to grip, right? So if you were to just use the rudder to turn the airplane with the wings level, the only thing that's gripping, so to speak, is the side of the fuselage. Well, that's not very much area.
Right on through.
It's just going to keep sliding. And besides which, then as you go, like in a car, when you go around an on-ramp or an off-ramp on the highway, you know how you feel pulled to the outside? Well, you'd feel the same thing in an airplane if you tried to turn without banking. So what we do is we bank the wings, and that does 2 things. First of all, that directs some of the lift from the wings sideways to help the airplane change direction, so that you don't have
this lift is pushing this
that
way.
lift is pushing the inside of the turn. And then it also makes it more comfortable for the passengers because you're not feeling pulled to the left or the right in the turn. But when you bank the airplane, some of that lift starts to go sideways, to help the airplane change direction, but that lift that's going sideways is no longer contributing to keeping the airplane up. So in order to keep from descending, you have to create more lift. Well, how do you create more lift? You increase the angle of attack. So when you're in a turn, you have to pull back, create more lift total, because some of that lift has to go sideways and some of it has to go up. And there's a good chart here on figure 5-34, which shows how as you direct more and more lift sideways, less and less of that lift is going upward, and you need more lift total to compensate for the fact that some of it's going sideways.
When we teach people to fly RC, when they do the turns, we always tell them to give them a little bit elevator to keep the nose up
And
through
exactly
the
the same thing in full-scale airplanes, and you'll see that happen as we fly. Now, as we pull back to create more angle of attack to help us create more lift in the turn, the centrifugal force that's pulling the airplane to the outside of the turn, or to be more
pushing you down.
to be more accurate, the airplane wants to continue in a straight line, and we're having to push it sideways in order to make it turn. As you say, your body also wants to continue in a straight line, and those wings are creating lift sideways to help the airplane turn, and that is making you turn by pushing on you through the bottom of your seat. So as you're in a turn, you pull back to create more lift to help offset the amount of lift that's going sideways to help the airplane turn. But as you do that, as the airplane turns, because you're banked, you're a little bit sideways, the force towards the outside of the turn, well, some of it's pulling down, some of it's pulling sideways relative to the airplane, but some of it's pulling down relative to the airplane because it's pulling sideways as a whole. So some of that weight, or some of that force, is pulling you down in your seat. And you'll see when we do steep turns that you'll feel pulled down in your seat. You'll feel heavier. And in fact, when we get to doing that, I'll teach you to judge whether your turn is steep enough or too steep by how much you're feeling pulled down in your seat. And you'll get to sense how much extra, weight you feel in your seat due to that turn is the right amount to have a nice stable turn just the way we want it.
Flying by the seat of your pants.
Exactly. Now, we talk about how an airplane moves through the air. We have a propeller, right?
Right.
Well, propeller is essentially just a wing moving in a circle, right? So you'll notice that propellers have sort of a twist to them, right? So one, as they rotate, that's twist is creating an angle of attack, just like it would with the wing. And it shows here in figure 5-44 in the book how you have your blade, the angle of that blade is called the pitch of the blade. And that is increasing your angle of attack, which is essentially making the propeller create lift, except since the propeller is, on the front of the plane aimed forwards, that lift is creating lift in the forward direction. Well, what do we call lift in the forward direction? We call it thrust, right? So that was something that very early aviation pioneers didn't understand very well. When the first propellers that were used on boats, and when they first started using propellers on boats in the 1840s or so, they thought about it as an Archimedes screw, which is an old, dates from ancient Greek times, a way of moving water up a hill. and they just applied that, put it on the back of a boat, and it moved the boat forward. Well, when they first started trying to fly airplanes, they figured, well, we can just take a boat propeller, and air is a fluid, right? So we just put a boat propeller on the front, and it's just sort of a flat paddle with an angle to it.
Didn't pull much air.
Didn't pull much air. So eventually, and this was one of the things that the Wright brothers realized that no one before them really had. It was one of the reasons that they flew where so many others had failed. They realized that the propeller was just a wing moving in a circle. And if you ever go to the Smithsonian Museum and you see the Wright Flyer there, you obviously can't get too close to it, but if you could, you can see that the airfoil on the propeller is exactly the same as the airfoil on the wing. Because once they'd found an airfoil that worked for their wing, they just said, well, it works pretty well for the wing. The propeller's a wing moving in a circle. We'll just use it there too. And it wasn't the perfect airfoil for a propeller.
No.
It's been
It's
improved.
better than anybody else had.
It's been improved on since, obviously, but it was good enough to get them off the ground.
It's better than anybody else had been using.
Yep. And then propellers have that twist of one blade relative to the other, but they also have a twist from root to tip. So if you look at a propeller carefully, you'll notice that it has a lot more pitch at the root than it does at the tip. And that's because, as you see here in figure 5-46, because the tip of the propeller has a lot further to travel, going around in a circle, it's moving faster. Well, if you're moving faster, you don't need as much angle of attack to produce the same amount of lift, right? So in near the center of the propeller, where the speed is not very high, you need a lot more angle of attack, versus out near the tip of the propeller, the blade is moving much faster, so you need a lot less angle of attack. And this difference in speed between the root of the propeller and the tip of the propeller can get so extreme that in some airplanes, like on high-performance aerobatic airplanes, or the T6 is the perfect example.
Yeah, that loud noise.
If you've ever heard a T6 flying at Oshkosh,
It's
it makes a lot of noise, and that's because the tip of the propeller is moving so fast that it actually goes faster than the speed of sound.
Yep.
And that sort of very harsh buzzing sound that you hear the T6s make, that's actually, 1,000 different sonic booms hitting your ear in quick succession.
It's a beautiful sound.
Mm-hmm. So, something else that we have to think about in terms of the propeller is, because the propeller is rotating, it introduces some other forces. So the propeller weighs a certain amount, right? If there's a propeller off an airplane and you lift it up, it probably weighs 15, 20 pounds, depending on the propeller. Well, that's a lot of weight to be spinning in a circle. And what happens when you have a heavy weight spinning in a circle? It becomes a gyroscope. So you get some interesting effects when you pitch the airplane. Because of gyroscopic precession, that force manifests 90 degrees in advance in the rotation. So, for example, if this model is a tail dragger, so if it's sitting on the ground and you raise the tail, as we do on takeoff, well, that propeller is a spinning gyroscope. It wants to resist, it wants to stay in the same orientation, it wants to resist that pitching. But because of the gyroscopic effect, rather than simply wanting to push the tail back down, that force manifests 90 degrees off, and that manifests on the left side, pushing the left side back, and that makes as we pitch the nose down, that makes the airplane want to turn left. And that's why, as we take off, when we raise the tail on the Chief, you'll notice you'll have to add more right rudder as the tail comes up, and that's part of the reason why. Now, you'll also notice as we climb out, you'll have to add more right rudder. That's partly because as the airplane has an angle of attack, the propeller is spinning, but it's the propeller is not perfectly perpendicular to the relative wind. It's on kind of an angle. So as this blade on the right side comes down, the relative wind is sort of coming up, right? So the blade actually has more angle,
Has more lift on this side.
has more angle of attack, and therefore more lift on the right side, and the blade on the left side is moving up. It has less angle, less relative speed as well because of the relative wind, and therefore the blade on the right side of the airplane creates more lift and more thrust than the blade on the left side. So essentially, the right side of the propeller is pulling harder than the left side, which tends to want to turn the airplane left, which means when we're climbing at a high angle of attack with a high power setting, so the propeller is working hard, the propeller is creating more thrust on the right side, turns the airplane left, which means you have to add right rudder when you're climbing because the propeller is pulling the airplane to the left.
Yep, I have that with the RCs.
Exactly. And then the other thing that's happening as the propeller is spinning, it twists the air. So we have we call the slipstream, the air moving past the airplane, we call the slipstream, and it twists. So as the propeller acts on the air, it'll push the air down on the left side and up on the right side.
Which is giving you more.
Right, so that the air that gets pushed down on the left side at the nose will come around underneath the fuselage in a spiral, and it'll hit the right side of the tail. Well, when it does that, if it hits the right side of the tail, that pushes the tail to the left. That pushes the
Plane more to the right.
more to the right. So as the twisting slipstream, I'm sorry, I had that backwards. So that would be for a left turning engine. For a right turning engine, the air is coming down on the left side of the airplane. No, it's down on the right side of the airplane. It's hitting the left side of the rudder. It's turning the nose to the left.
To the left.
So all of these things, the gyroscopic precession, the blade on the right side producing more thrust, and the twisting slips, and we call that P factor, by the way.
Yep. I'm familiar with
The blade that produces more lift when it's moving downwards and pulling the nose, we call that P factor. But the twisting slipstream, as the air comes down on the right side and around up on the left, hits the left side of the tail, pushes the nose
to the left.
All three of those things are pushing the nose to the left.
You're fighting her hard with the rudder.
Right, which means all those things require right rudder to counteract. So when we're climbing, that's why we have to add a fair bit of right rudder.
Makes a lot of sense. I've experienced that with RCs. Almost all my Warbird takeoffs go to the left.
Yep, exactly.
It's a balancing act to get it right.
And that's why.
I get yelled at sometimes because the flight line's on the left. And I fly over people, and it's not a good thing.
So, one final thing to talk about here is we've talked about pitch, we've talked about roll, we've talked about angle of attack, we've talked about how as we have to create more lift due to the airplane changing direction, that creates more angle of attack to create more lift in order to help the airplane change direction, either pulling out if we're nose down. If we want to pull up, that creates we have to create more lift to change direction. If we're turning, we have to create more lift to change direction. And that feeling of being pulled down in your seat, we call that a G loading, G for gravity. So because you're feeling pulled down in your seat, well, so is the rest of the airplane. And that is essentially making the airplane feel like it's heavier. And you have to create more lift to counteract that. But that means that the wing has to support all that extra effectively it's supporting more weight, right? So the wing is only so strong, so how much of that extra can it support? Well, for most airplanes, they have to be able to support 3.8 times their own weight with a 50% safety factor. So 5.7 is the ultimate failure load, but we add a 50% safety factor, so we can't pull with more. We can't feel more than 3.8 times as heavy as normal. Now, trust me, pulling 3.8 Gs is in an airplane, you'll feel it. You know, if you ever do aerobatics, you'll get up towards 3.5 to 4 Gs there. And aerobatic airplanes are designed to be stronger. Do
the fancier planes like that have G meters in them?
They do.
Cool.
My
I know, like Red Bull air races, they're
Yep.
not allowed to go over 10.
Yep.
I don't even want to think about that.
Yep. The most I've ever done is about 6 in an aerobatic airplane, and that's quite a bit.
It's enough to hurt.
Yeah, it doesn't hurt at that point yet, but it's enough that you feel it in your seat for sure. But we can only support so much of that, right?
Mm-hmm.
So on figure 5-55 here, we have our operating envelope, they call it. So this relates our speed to our load factor, or our G load. So you'll see the green zone is where we can fly. The left side is the stall speed. The right side is the maximum speed for the airplane. You'll see maximum structural cruising speed. So that's sort of your maximum speed in rough air. Then you have a caution range, and then you have your never exceed speed. There's a red line up here. Okay, and if you go faster than that, all kinds of bad things can happen.
It's not a good idea.
Control surfaces can develop vibrations. We call it flutter, which that can actually do things like stretch control cables or even break hinges on controls. So you don't want to go that fast. But in this green range, you have that speed from your stall speed on the bottom to your never exceed speed on the top. And then you have your G load, so all the way up to your maximum. In this example, it looks like they're showing about 4.5 Gs as the limit load. So that would be more like a utility airplane. And in fact, the Chief is designed a utility category. So this would be very much like what you'd see for the Chief. So 4.5 Gs at the top there, or just under about 1 3/4, 1.7 Gs on the bottom there on this graph. So you don't want to pull more G's than that, because that's as much weight as the wing can support. Now you'll see that you'll have a couple things marked here. So at the bottom here you have your normal stall speed at 1 G. As you increase the load factor, your stall speed goes up, right? And then you have maneuvering speed. So up here at this graph is where the accelerated stall line intersects the maximum G loading, right? Well, what exactly does that mean? I mean, we can talk about graphs all day, but what does this actually mean to us as pilots? So the maneuvering speed of an airplane, the way the FAA defines it in this book, Pilot's Handbook of Aeronautical Knowledge, is the speed below which full and abrupt control movements may be made without damage, okay? That's the official definition, but what does that mean? So, to explain that a little bit more, the faster you're going, the more the air wants to stick to the wing, right? Because as you get down to stall speed, it wants to separate. But the faster you go, the more it wants to stick to the wing. Therefore, the faster you go, the more G's you can pull before the airplane stalls, right? Well, maneuvering speed is the speed below which you will stall the wing before you overstress the wing, right? If you're above maneuvering speed, the wing will fail, or at least become overstressed, before you stall. So above maneuvering speed, you can theoretically pull enough G's without stalling to overstress the wing and potentially pull the wings off the airplane.
Yep, done that on a RC plane too.
Yep. So that was
Quite epic.
that was the result of maneuvering above maneuvering speed on an RC.
Yeah, we do that a lot. In the RC world, it's pretty popular. It's kind of a fun thing to do. At least it's fun to watch.
A little less fun when you're sitting in the airplane.
Yeah,
isn't
but if you're
it?
sitting in it, not so much.
Yeah. So the way I like to define maneuvering speed, which I think makes a little bit more sense intuitively than the official definition of the speed below which full and abrupt control movements may be made, is maneuvering speed is the speed below which the wing will stall before you pull the wings off. Speed above which you can theoretically pull the wings off without stalling. Now, that means that if you're below maneuvering speed, the stall is essentially acting as a safety valve, where if you pull too much and you're in danger of overstressing the wing, well, that wing will just stall instead of becoming overstressed. So it works kind of like a safety release
That's good.
of air pressure.
That's good.
But if you're above maneuvering speed, that safety release is not sensitive enough, and you can therefore, pull enough G's to overstress the airplane. So that's how I like to explain maneuvering speed. Does that more or less make sense to you?
Yeah, you go too fast, you mess things up.
Right.
Right. Yeah.
But specifically, why? So now, maneuvering speed is interesting as well, because maneuvering speed changes depending on how heavy the airplane is, right?
Mhm.
So intuitively, what would you think happens to maneuvering speed as the airplane gets heavier?
You would think it would have to be faster.
And you're exactly correct. Can you...
Because you've got more weight to pull around, so to make the control surfaces sensitive enough, you got to have more speed going over them. Sort of.
Partially, but what I'm really getting at is, remember, what we're concerned about is not so much maneuverability. We're concerned about is the airplane strong enough to withstand what we're doing to it.
Mm-hmm.
So think about maneuvering speed as the speed above which you can theoretically pull the wings off. Okay. Well, if the airplane is heavier, does that speed that you can pull the wings off at go up or down?
The speed would go down because you've got more weight pulling.
You would think so, but you're actually not right.
Really?
It actually goes up.
Well, I'm glad I answered it the way you expected me to.
Because what happens is, so if you're at a very light weight, right?
Mm-hmm.
It doesn't take much angle of attack to create that amount of lift, right?
Mm-hmm.
So when you start pulling and you start increasing that angle of attack, you have a long ways to go increasing that angle of attack before that wing stalls and that safety valve activates, right?
Mm-hmm.
So then the harder you can pull without that safety valve activating, but by the wing stalling, the more G's you can pull, right?
Mm-hmm.
So whereas if the airplane's heavy, it's already taking more angle of attack to create that greater amount of lift, right?
Mm-hmm.
So let's say if the airplane weighs 1,000 pounds, let's say the wing stalls at 10 degrees angle of attack, okay?
Mm-hmm.
The airplane at 1,000 pounds, let's say, needs 4 degrees angle of attack to create that much lift, okay? Well, that means you have 6 degrees more angle of attack that you can add before the wing stalls, right? Well, now let's say the airplane weighs 2,000 pounds, and now let's say it takes 7 degrees angle of attack to create.
You only got 3 more.
You only got 3 degrees to go, so how hard do you have to pull to add 6 degrees of angle of attack? Pretty hard, right? How hard do you have to pull to add 3 degrees of angle of attack?
Not much.
Not so much. And remember, the harder you pull, the more stress you're putting on the wing. That makes sense? So if the airplane's heavier, you don't have to pull as hard to get it to stall. If you don't have to pull as hard, you're not putting as much stress on the airplane. If the airplane's lighter, you have to pull harder to get the wing to stall. You pull harder, you're putting more stress on the airplane. And remember, if the airplane's lighter, you have to pull harder. If the airplane's heavier, you don't have to pull as hard to get it to stall.
Because you're already there.
Because you're already there. And therefore, if the airplane's light, you have to pull hard to get it to stall, which means that you're putting more stress on the airplane. That equates to a lower maneuvering speed, right? If you're heavy, you don't have to pull very hard to get it to stall. That equates to less stress, and that means your maneuvering speed can be higher when the airplane is heavier.
Interesting.
It's counterintuitive on the face of it, but when you start thinking about it,
It makes sense.
starts to make sense.
Once you explain it that way.
That's something that took me a while as a flight instructor to find a way of explaining it to people that
Is that
actually
something
makes
you
sense.
can actually show in the plane? Well, probably
Yes.
don't want to be going too fast, but
Well, we can definitely show. Well,
be kind of hard because we're probably close to the
we're
limit of the chief.
right, and
anyway.
we're close to gross weight anyway. And since this mainly varies depending on how heavy you are, I mean, if you went up and you did stalls with the 2 of us, and then after you solo, you go up and do stalls by yourself,
Then it'll be different.
you'll notice a difference, right? So that's
There's a lot in that
that's
chapter.
the concept of maneuvering speed. Now they talk here about how their radius of turn is higher at a higher speed, which makes sense, right?
Right,
Because
pushing farther out.
right. So that and if you're curious about that, figure 5-62 and pages 541 and through about 543, 544 goes into that in more detail. But that's a fairly easy concept to grasp. If you're going faster, it takes more space to turn around than if you're going slower.
That makes
And that gets into, if you're flying in the mountains, knowing your optimal speed to have the tightest radius of turn if you get stuck in a canyon or something and have
and
to
you
get
gotta
out. That's something like the fat tire cowboys and stuff, the flying cowboys have to deal with flying out in Idaho like they do.
Those guys are nuts.
If they get stuck up in a canyon or something, they have to know the best speed to fly to get back out of it again. But flying here in the flatlands of Wisconsin, it's interesting to know,
Right,
your
but
optimal
we
speed for
aren't
the
gonna
tightest
experience it
radius of
here.
turn, but it's not something that we have to deal with terribly much. And in the end of chapter 5 here, they get into talking about the physics of flying near the speed of sound. Above about Mach 0.7 or 70% of the speed of sound. Now, when I'm at work flying the jet, I fly at around 74, 75% of the speed of sound, but Chief can't go anywhere near that fast, so we're not going to worry about that just for now.